Hi everyone. Today I'm going to talk about the paper AlwaysSafe Reinforcement Learning Without Safety Constraint Violation During Training, which was accepted at AMAS 2021. My name is Thiago and this is joint work with Nils, Jansen and Matthijs Spaan. So let's get started. Reinforcement learning algorithms have been collecting many achievements. These algorithms are able to play chess, Go, and even Atari, but there is still a large gap between these applications and real-world tasks. And there are many challenges preventing us from closing this gap. Among them, we have safety constraints. So how can we train a reinforcement learning algorithm to perform a certain task without violating these safety constraints? Let's consider, for example, this electric taxi. In this case, we can move around the grid, pick up the passenger in a certain position, and drop the passenger into its destination, in which case we get a reward. But this taxi has a battery, so if we run out of battery, we can get stuck in a certain point. How can we train a reinforcement learning agent to perform the task of delivering the passenger without letting the taxi run out of battery? One option would be to augment the reward function by giving a penalty for running out of battery. However, this creates a burden on the designer of the system that would need to decide how to balance between the task at hand and the safety constraints. So one option is to create an extra signal that here we're going to call cost, that is going to serve as a proxy for the safety constraints. Instead of assuming that the environment is described by MDP as in typical reinforcement learning settings, here we are going to assume that the environment is described by a constrained MDP. So during the interaction with the environment, the agent observes both the state, the reward, and a cost. The objective is almost the same. We still want to maximize the expected return. However, we want to keep the expected cost below a certain threshold, C hat. We can solve a constrained MDP using a linear program that computes the occupancy measure of each state action. The occupancy measure is essentially the expected number of visits to a certain state action. We multiply the occupancy measure by the reward to obtain the expected return and multiply it by the cost function to obtain the expected cost. Then we just need to include some extra constraints to ensure that the occupancy measure respects the transition function. However, in reinforcement learning, we don't know the model, so we need to explore the environment to learn the optimal policy. Here, we use optimism in the face of uncertainty to decide between exploration and exploitation. Using the previous experiences, we can create an uncertainty set that contains the true constraint MDP with high probability. Now, when we are solving the linear program, we can allow the agent to choose which of these transition functions inside of the uncertainty set it wants to use to compute the occupancy measure. Also following the optimistic strategy, we can use the upper bound of the reward function and the lower bound of the cost function. An agent following this policy has bounded regret both in terms of performance and safety. However, in the early episodes, this policy might be unsafe. So, how can we compute a policy that is guaranteed to be safe? Returning to our taxi environment, we may notice that not everything is relevant for safety. Consider, for instance, the position of the passenger. This information does not influence the position of the taxi or the amount of battery we have left. Therefore, when we are reasoning about the safety dynamics of this environment, we can ignore the position of the passenger. More generally, we consider that we have access to a cost model irrelevant abstraction. Intuitively, this is a function that groups states that have similar safety dynamics. Therefore, when we compute a policy on the abstract constraint MDP, the expected cost of that policy is going to be the same both on the abstraction and on the ground constraint MDP. Assuming that we have access to this abstraction of the safety dynamics, let's see how we can compute a policy that is guaranteed to be safe. First, we augment the linear program that we've seen before, including a new variable z. This variable is going to control the occupancy measure of the abstract constraint MDP. Since we know the dynamics of the safety abstraction, we can bound the expected costs of this occupancy measure. Finally, we can tie the occupancy measure of the abstract and ground MDPs. A solution to this LP induces two policies, one abstract policy and one ground policy, which have some interesting properties. The abstract policy is guaranteed to be safe, since we know the safety dynamics when we are computing it. However, since it ignores parts of the environment that are relevant for the reward, it might be suboptimal. While the ground policy, although it might be able to reach an optimal performance, has no safety guarantees, as we've seen before. To get the best of the two worlds, we propose a method that dynamically adjusts the safety constraints. The idea is to compute a ground policy that is guaranteed to be safe in the whole uncertainty set. To find such policy, we can adjust the safety bound, which makes the policy more conservative. We can repeat this process until the policy is actually safe in all the constrained MDPs of the uncertainty set. If the uncertainty set is still too large, the constraint can become very tight, making the problem infeasible. In this case, we can still deploy the abstract policy to collect more data and reduce the uncertainty set. Now, let's have a quick look at some of our empirical results. On this plot, we set the bound on the expected cost to 0.1. We notice that both optimistic approaches do not respect the safety constraints, while the AlwaysSafe approach, using the abstract policy and the dynamically adjusted policy, remain below the safety threshold. On the right, we see that the expected return of the abstract policy is actually suboptimal, while the dynamically adjusting strategy can eventually reach the optimal policy. Constraint reinforcement learning is an interesting approach for safe reinforcement learning because it models the safety requirement explicitly, avoiding the issue of defining a reward function that balances safety and performance. The algorithm we proposed exploits some prior knowledge about the safety dynamics of the environment to ensure safety during the learning process. It seamlessly can switch from a conservative and safe policy to a grid policy that has potential to reach optimality. Finally, this algorithm can still explore optimistically. And this is it. Thank you for listening.